In this video, we're going over the concepts for Chapter 7, which is titled Chemical Equilibrium, Acids, Bases, and Buffers. In the beginning of this chapter, we are going to learn about the principles of chemical reactions. Chemical processes are often governed by either kinetics or thermodynamics. Let's learn what those terms mean. Chemical kinetics refers to the study of the rates of chemical reactions. Chemical thermodynamics is the study of the changes in energy that take place when processes such as chemical reactions occur. In terms of thermodynamics, whenever we talk about this property, we often also refer to the concepts of enthalpy. And enthalpy is defined as the sum of internal energies plus the product of pressure and volume. In general, when we're looking at a reaction and we're looking at its enthalpy, we're just looking at the difference in enthalpy between the products of the reaction and the reactants. Next, this energy, depending on if is emitted or if it's absorbed, we have terminology to define it. And in figure 7.2, we have illustrations that define these two processes. First, if we have a reaction that is considered endothermic, an endothermic process is when we have a reaction that requires heat or heat is being added or absorbed in the system. On the other hand, if we have an exothermic process, that means that energy specifically is given off or there's a release in energy. In other words, there's heat that is going to be produced in the reaction. Whenever we look at a reaction, overall, we can actually plot what are the differences in energy when a reaction progresses. And all of this is illustrated in what is called an energy diagram. In figure 7.3, we can observe the energy diagrams for exothermic processes, that's in letter A, and also an example of an endothermic reaction in letter B. What we can observe, and I'm going to zoom in first at letter A for an exothermic reaction, is that overall, in the reaction as it progresses, the average energy of the reactants is higher compared to the one of the products. As these reactants come together, they have to overcome an energy barrier in order to get to products. That's what's known as activation energy. And you can see that the definition of activation energy is the energy needed to start some spontaneous processes. If now we look close to an endothermic reaction, the average energy of reactants is actually lower than the average energy of the products. And if we look as the reaction progress, how different in an endothermic process the energy diagram looks, then we can observe that the activation energy appears to be higher when we compare it to the activation energy of an exothermic process. Overall, when we look at the enthalpy of the reaction, understand that the enthalpy of reaction is here because it's the energy difference between reactants and products. When we referred to kinetics, we introduced it as the topic that actually looks at how fast the speed of the reaction. When it comes to the collision model of kinetics, this model is going to explain how specifically when a chemical reaction can occur, it will only happen when the reactant molecules, atoms, ions that are present in your reaction collide together with the proper orientation, and they're going to do so when they exceed the activation energy in order to get to products. Overall, we see that this model is based on the following three assumptions. First, reactant particles must collide with one another in order for the reaction to occur. These particles must collide with at least a certain minimum total amount of energy if the collisions want to result in a reaction. Lastly, in some cases, these colliding reactants must be oriented in a specific way for a reaction to happen. Only if all three assumptions are met, then the collisions are defined as effective collisions, and then the reaction occurs. Let's look closely at figure 7.4, where we have the example of specifically ineffective collisions versus effective collisions. In letter A, we can see how nitrogen monoxide is going to react with O3, which is called ozone. And if these two reactants meet and there's an ineffective collision, we see that the product of the reactions is just the reactants separated. So there's actually no product. You're just regenerating your reactants. But then, if again, your nitrogen monoxide and your ozone have an effective collision, meaning they meet with each other, with each other with enough energy to overcome the activation energy, then we see that when in the right orientation, I should also say, then we see that overall this is an effective collision, and we see in the reaction the formation of the product that in this case it happens to be nitrogen dioxide and molecular oxygen. Since whenever we're looking at kinetics, this is related to the rates of the reaction, meaning the speed of the reaction. There are three factors that affect the rate of a reaction. Those factors are number one, the concentrations of the reactants in the reaction. If you increase the concentration of reactants in the reaction, because now you have more molecules that can collide, as long as they meet the three parameters that we just talked about, we will see that there's an increase in the speed of the reaction. Another factor that affects the rate of the reaction is going to be temperature. And when it comes to temperature, because it is known that an increase in temperature is going to increase specifically the kinetic energy in the molecules, that can lead to more collisions with the correct activation energy that can be overcome in order for those reactants to make products, and that's how the speed of the reaction can also be increased. Lastly, the presence of a catalyst can increase the reaction rate. But when it comes to catalysts, it is very specific how they are going to increase the rate of the reaction. In the case of catalysts, they specifically are going to increase the rate of the reaction by lowering the activation energy present in the reaction. In figure 7.5, we can actually observe how the presence of a catalyst can lower the activation energy. Overall, what we see here is that there is a reaction that is happening, and then we can see it here by the segmented lines. Overall, a catalyst does not change the reactant energy and the product energy. That's why, in a way, we lose the trace in this area also, because the catalyst is not affecting the energy of the reactants or the energy of the products. We can observe overall in this lavender line that now the activation energy hill is going to be lower with the presence of a catalyst. In later chapters, we're going to see how the presence of a catalyst is necessary in order for some reactions to occur. Lastly, inhibitors, which we mostly will see in the chapters leading or related to, is what I'm trying to say, with biochemistry, are going to be substances that actually decrease the reaction rates. So we will talk about inhibitors later in the semester. Now we are going to proceed to talk about chemical equilibrium. All reactions in principle can go in both directions, meaning the reactants are going to come together and form products, and the products can essentially return into forming the reactants. When a reaction happens in this manner, then we say that the reaction is in a state of equilibrium. When this happens, we consider that the reaction system, in the conditions that it's present in the reaction, are going to permit that the rate of the forward and the reverse reactions are going to be equal. When we look at the figure 7.8 and we look at the illustration on the left, we can see that we have the example of H2 plus I2 forming HI. In that reaction, we can see that the formation of the product, overall, the rate is going to become equal with the rate of the product going into the reactant. Another observation in equilibrium systems is that when it comes to the concentrations of the reactants in the products, we see that overall they are not going to change and they're going to become constant. So if we observe over time what happens to the concentration on specifically the illustration that we have on the right, we see overall that as the reactants are overall reducing in concentration, they become constant. And then as the product is forming, it also becomes constant. Since in this reaction, it will form HI, and that HI is going to turn back to H2 and I2. That's why this system is considered to be in equilibrium. When a system is in equilibrium, Le Chatelier's principle is going to explain to us how the rates of the reactions are going to be shifted in order for the system to reestablish an equilibrium. The factors that will be affecting the equilibrium systems that we are going to be studying in our course include the changes in concentrations of reactants and products, and changes of reaction temperature. We can observe specifically in figure 7.11 how we have an illustration of N2O4 forming NO2. This equilibrium reaction actually depends on temperature. We can observe that when in a sealed tube, we have these molecules. If the vessel is cooled, then it favors the formation of N2O4. While if the same sealed tube is heated, then is going to favor specifically the formation of NO2. And this is just an illustration of how temperature is going to affect the formation of the product or the reactants. We are going to observe in a moment that if you increase the amount of reactant, meaning its concentration, What happens overall that this is going to shift towards the product side of the equilibrium reaction. Well, if you increase the concentration of the product, then this is going to favor the reverse reaction, and meaning that now the reaction will shift towards reactant. All of this is going to happen in order for the system to regain equilibrium. We can observe that overall, all the observations for concentration and for temperature have been summarized in table 7.1. We can see that here we have listed the different factors in terms of concentrations, meaning removal of reactant, addition of reactant, removal of product or addition of product. And then in the last column, we see how this shift towards the reactants or the products. Remember that if the shift is towards reactants, that refers to the reverse rate, while if things are going to be shifting towards the products, that means that that is the forward reaction. Additionally, we have how temperature is going to affect specifically a reaction. When temperature affects a reaction, understand that we need to pay attention in the reaction if we have an exothermic process or an endothermic process. Because what happens is, as we can see in table 7.1, that if we lower the temperature of an exothermic process, that is going to shift the equilibrium reaction towards the product. But if we raise the temperature in an exothermic process, then what happens is that the shift goes towards the reactants. On the other hand, if we have an endothermic process, if you lower the temperature of a system like that, then what's going to happen is that it's going to shift the equilibrium towards the reactant. But if you raise the temperature of an endothermic process, then the shift is going to be in the directions of the products.